Okay, so this week in recitation you'll see your free response. You'll go over the free response to the exam in recitation, and then I'll be getting the Scantron results back this morning probably, and we'll be putting all that stuff together and getting you a score in the next couple days. Okay, so yeah, let's move on. So we were talking about arc length last Wednesday, and so let's do an arc length example here. So what was the idea with arc length? So we want to know, say, starting from 0 to some value of x, what's the distance along the curve? How long is the curve? That's what we mean by arc length. So let's actually do this. This switches over. All right, so I have that graph I just showed you here. And we're going to do it by hand first. So I've got a string, this, okay? So I'm gonna do it by hand, and then we're gonna get an estimate, and then see if our arc length function, that we came up with last time, how it does. Okay, so I'm gonna do my best here to lay the string along the curve. I'm going to go up to 5, from 0 to 5. So on like this, and then right about to there. Okay, so I got my thumb where I think 5 is. Now I'm going to lay that out on the x-axis, and I get, what do I get? 11.6? 11.5? Something like 11.5. That's what I got when I took this string and I laid it out from 0 to 5. So let's go back to this. And so how can I find out exactly how far it is along the curve starting at x equals 0 to x equals 5? What can I do? So I know it's been 5 days since we talked about that, but anybody remember? Okay, yeah, so we derived this arc length, accumulation of arc length formula. And to get the accumulation of arc length, what did it take? Well, if we want accumulation of arc length, we needed, what's the key thing that we need? Every time we want to do an accumulation of something, we need its rate of change. So last time we derived this rate of change. So we're going to do, we'll call this SF. So little s means arc length. Little s means some length of arc. So this is the arc length for the function f. So we'll do that. Control 9 of x is going to equal. So since we're starting at 0, we don't need to include this s of 0 term. Okay, we can let's just do the integral. So Control Shift I, and we're going to integral from what to what? 0 to? No, we want the function, guys. So remember, the function can tell us any, and then later we'll figure out what s of 5 is. But the function is the most powerful thing, because now given any value of x, it'll give us arc length. So yeah, 0 to 5 would work, but let's just write out the whole function. So then, what was the rate of change of arc length? Remember how we did it with the Pythagorean theorem? Ready? It was remember the Pythagorean theorem was square root of 1 plus the rate of f, right? The rate of f. So to get the rate of f, what do we need? We need the derivative of that. How are we going to get the derivative of that? This long polynomial times e to the minus x. What does it take to get to the derivative of that? Remember from Calc 1? Product rule, okay? No fun. That's why we like GC, because we can define a function, the rate, and we can just say, all right, you do the derivative for me. So total derivative of and so now we've just assigned the derivative of f to be the rate of change function of f. And so now what can I put in here? Instead of having to do all that product rule, what can I put here? R sub f of x, R sub f of t, and we need that thing, what? That rate of change of f was squared. And then dt. And now we want to check what I came up with. We came up with about 11.5 along the curve from here to 5. So how do we verify that? S sub f of 5, right? Function notation. S sub f of, here's the, look at that. I think I said 11.6 first, didn't I? All right, so we said 11.5. So there it is. All right, what if I want the length of the curve? I want to use this function, S sub f of x, to find the length of the curve from, say, 1 to 4. So what if I wanted now starting from 1 to 4, and I wanted the length of that length of curve? Yeah. Yeah, huh?
S of f 4
Uh-huh.
minus S of f.
Yeah, so this is the amount of change, right? A big amount of change is just the final amount of your quantity minus the initial amount. Is the amount of change. So we can do S of f of 4 minus S of f of 1. So that just told us that starting from here along this curve to x equals 4, so starting from x equals 1 to x equals 4, that length of the curve is 3.64. Okay, how can I do this a different way? So we talked about how can I do this a different way? So I can revise this function. We mentioned this, but we haven't really practiced it yet. But I can revise this function to be the arc length, not just starting from 0, but starting from any x value. Remember what we said? So let's, instead of having just the one argument that's the independent variable, we can have two arguments, one of them being the starting x value and the other being the independent variable. Okay, so I can come in here and say a So now, we still only have one independent variable. That's x. That's x is changing. But now we want to be able to specify our starting value instead of it always being 0. So how will I change the function? Change the 0 to a. So now whenever I call on the s, I use function notation to call on the s of f function. It needs two things, right? It needs a first value, which is going to be a starting value, and then it also needs whatever, if you're going to choose a specific value of x. So to get what was used to be s of f of 5, I want to do what? 0, 5 now, because that's the way that it's defined in GC. As first tell me the x value where we start, and then tell me how far you want to accumulate to, right? So now how can I redo? So this was what, 0, 4 and 0, 1. And there's the 3.64. But now that I've defined s of f of is a and x, so s of f of x as given the two arguments, I got an easier way to do the second question. How can I represent and find the length from 1 to 4?
So that's 1 to 4.
Yeah, so now let 1 be that starting value, and then x be 4. So if I do s of f of, function notation, guys, this is powerful stuff, 1, 4. get the same thing. Okay. And then make sure you go back and review. I know it's been 5 days, but you got to go back and review the derivation of that rate. It was based on the Pythagorean theorem, but you got to know that for the next test, as well as just being able to use the rate of change formula. Sorry, use the accumulation of arc length formula to generate just curve lengths. Okay, but make sure you know the derivation of that rate of change that we did last Wednesday. Question on arc length. So the homework problems are pretty easy. They're just applying the formula and finding some different arc lengths, but then explaining the meaning of the symbols. Okay, so it's pretty straightforward. There's nothing too bad in that. So there will be a homework due Wednesday. It'll be like half as long as usual. Okay, so there will be homework. I'll put it up today. It'll be like a half homework, and it'll include some arc length problems. Questions on arc length? Okay, so then let's move on to surface area. So we're going through these different applications of our integral of accumulation. So integral is about the net accumulation of a quantity, and we can talk about lots of different quantities. What have we talked about so far? We talked about area between the function and the x-axis, and we found out that if you just look at the integral, you're going to get signed area, right? You're going to get signed area, and then we talked about how to get actual area, and then we've talked about arc length, and so the next thing we want to talk about is surface area. So just like we generated solids of revolution and found their volume, so that's the whole. We spent a lot of time on volume, right? So we found accumulation of volume. So we can also, here's a curve, this red curve. When it's rotated around the x-axis, you get this wavy kind of, I don't know, horn-looking solid here, like that. And so what about not the volume anymore of that? If we filled it up, right? We got the empty shell. We could fill it up with cylinders and find the volume. We know how to do that. But what about the surface area of this thing, of the empty shell, right? So you got this empty shell. What about the surface area of that? Okay, so if S, capital S, all right, so we're going to use a little s means arc length. Big S, capital S, is going to be surface area, okay? So if S is the surface area function for the surface, what does capital S of A, X mean? All right, first of all, what does it mean? And then can you write a general rule for how you would define such a function? All right, so what does capital S of A, X mean? And then could you write just in general what the general structure of the accumulation of surface area function will be, how it will be defined? Okay, so I'll give you a couple minutes for those two questions, and I'll start attendance. But everyone's talking to someone about this, okay? Okay. All right. So let's regroup here. What does S of A, X, what will that mean? What will the meaning of S, A, X mean? Did I turn that around? So you haven't used it yet. She said the total surface area, so S, A, X. Say it again. What is it?
Oh, I said that would be the total surface area of whatever the chosen starting value of A is to the ending value.
Good. She says the total surface area from whatever our value of A is, our starting value of A, up to X. This will be the surface area of this thing, the shell that we had created, starting from A up to X. Good. Okay. And so then what about a general structure of defining that function? Did you come up with that? Dylan. Yeah. Integral, okay.
from
A to x.
2 pi f of t dt.
Okay, and what is that? So we haven't gotten there yet.
Okay.
What is that thing you just said in general?
That's the rate of change of the solid thing.
Rate of change of, what are we accumulating?
The area.
Surface area. Big S, right?
Yes.
Then?
D, or of t dt.
Yeah, so this is going to be the structure. Same as always, right? Now for accumulating surface area, we need the rate of change of surface area. And then once we have the rate of change of surface area, oh, I broke it. Yikes. Snap in there. Is it still usable? Let's see here. Okay, still use it. Okay, so yeah, so this is the same thing we've done over and over again, right? If you want to accumulate surface area, what do you need? You need the rate of change of surface area. And this is what our net accumulation of surface area will look like, starting from A up to X, right? So this is what you should have come up with. All right, so now we got to figure out what is the rate of change of surface area. So let's take a look here. Which one do I want first? I think I want this one. Yes. Okay, so let's look at this example. And this is our, what, rotating sine x from 0 to pi around the x-axis. We've seen this before. And when we rotate that thing, we make this shell, right? We make the shell that looks like this, right? I didn't want that. Let's see. Wrong axis. Hold on. Here we go. I want to rotate around the y-axis. There we go. All right. So when you rotate that thing around the x-axis, we get this empty shell, which is something like a seed pod or something like this, right? Like or a lemon drop or something. I don't know. But we want that. We want the surface area of that, or a function that will give us the surface area of accumulation starting from 0 along this way. All right, and so what did we do before with the solid? We filled it up and we found accumulation of volume of filling that shell, but now we're interested in the surface area of the shell itself. Okay, so not that one, I want this one. So let's look at that, what we did when we filled up the shell. Okay, so here's filling it up with cylinders based on delta x intervals or delta y intervals? Delta x. And in this case, what was our rate of change of volume? So if we use delta x intervals and we fill those delta x intervals with cylinders starting from 0, what was our rate of change, remember? You said area of the base, right? So that black area, right? That black area, the area of that black circle on the far right side would be our rate of change of volume. So now if we're thinking about surface area, what would we do? What would we say for that? So now rather than generate volume with that black face coming out, what instead would generate, if we're thinking in the same line, along the same lines, what would generate surface area? Yeah, so it's like what geometric thing is increasing that's forming the surface area, right? And that edge is the rate of change. So what'd you say, Josh?
I was saying that as the height increases, we're looking at the purple region for each current interval.
The purple region. Okay, so the purple region is like a little bit of surface area. So what would be the rate of change of surface area? Yeah, so looking at the purple region, but that would be like an actual little amount of surface area. What would the rate of change be? If we follow the same logic that we had before. Because remember, what was the rate of change of area? What was the rate of change of area? So this is A. What was the rate of change of area as x increased? The value of the function. So it was like this length of this edge is like how much the area is changing by if you increase x a little bit, like per unit, right? That's the rate of change. So in the same way, if we're accumulating area, what would the rate of change be? Anyone see what it would be? Someone, yes. Like the circumference of that circle, right? So if we want to generate volume, we take the whole area of this black. But if we want the, let's see. Yeah, if we want the surface area, then the rate of change is just going to be what? The outer edge of that black disk. And that's going to be the rate of change. So we think maybe the rate of change is circumference. And what is circumference? 2 pi r. And so in this case, what is r? Is it an x coordinate, y coordinate, big change in x, big change in y? What is the radius of that circle? Just the y coordinate, right? It's just the y from the x-axis up to the curve, it's just the y coordinate. So 2 pi y. All right, so, and in this case, that would be 2 pi if we wanted sine x. Okay, so, is it right? Is it, it's consistent with what we've done before, right? It's consistent with what we've done before. So this outer, like, ring, as that ring grows, that's going to be our rate of change of surface area. Just like this line was our rate of change of area, and that black disk was our rate of change of volume. Okay, so let's test it out with something that we know for sure what the surface area is. So we don't know what the surface area of this seed pod is. It's kind of a weird shape because it's based on sine. But what if we did a sphere? So what if we created a shell that was a sphere? Then we could test this. We could test our rate of change function against what we know already the rate of change or the surface area of a sphere is. Okay, so let's look at that. All right, so here's same kind of deal, but this curve is the curve of the circle 9 minus x squared. So that's and then when we rotate that around the x-axis, we're going to get a sphere that has radius of what? What is this circle? Its radius? 3. So this is circle radius 3, rotated around the x-axis, we're going to get a half sphere of radius 3, right? And so then what is the surface area of a sphere? Does anyone remember? 4 pi r squared. And so if we go from 0 to 3 of this shell that's rotated around the x-axis, what will the surface area, we know what that surface area will be because it will be the surface area of half of this. So the half sphere will have a surface area of 2 pi, and what's our radius? Our radius is 3, so is that 18 pi? Okay, so we're going to test out, and we came up with a rate of change function for surface area of, what, 2 pi y. So we want to test that out. If we accumulate surface area from 0 to 3 using the rate of change that we came up with, then we're checking to see if we're going to get 18 pi. So here it is. So what did we think? We said integral from a to x of I can't get it. Try again. Yeah, that'll start there. It's giving it to me. Okay. All right. A to x, and then what did we? Gee whiz. Come on. I can't. It's not letting me click in there. It's probably because this is running. Now I bet I can do it. There we go. Okay. All right. So a to x. What do we think the rate of change was? 2 pi. And what is y? F of x, right? So f of x. So I'm going to do f of t dt. And then here's 18 pi. 18 pi is 56.548. And what do I want to do? I want to do capital S of HS 0 2. And is it 56.548? No. It's smaller. So we know the actual surface area is 18 pi. When we test out our rate of change function that we thought might be right, we got something significantly lower. So something is wrong. Something is wrong with our approach here. Something's wrong with our rate of change function. So let's take a look at this. What is wrong with this? Why is this rate of change function not? I'll make delta x a little smaller. Why is this rate of change function not getting us the surface area? Does anyone see why? Yeah.
Do we have to account for the edges? Like at the ends of it?
Not quite. It's more what's happening in the current interval. So what were we saying? We're saying the rate of change is based on. Okay. What's that? Yeah, do you see? So what we're doing when we're accumulating this way, using just the radius, we're just basically looking at this thing as it grows horizontally. So we're getting this stair step, but we're not, really what we need is to use what we've learned before here. So we don't want to use a disk that goes like this, right? So remember what we did with surface arc length. So here's a big delta x interval, say from here to here. Oh, here to here. Remember we had dx. And we had dy, and then we had what? ds. We used the dx change in the current interval to try to come up with surface area. What should we use instead? ds, right? It doesn't. ds is what's going to model the surface area. dx, as things get small, just looking at that horizontal change, is not going to model this thing that's doing lots of things besides horizontal change, right? So by using ds, which we found by arc length, That's what we want to use to model surface area. And is it going to give us a larger result or a smaller result than dx? Larger, right? The hypotenuse is larger than dx, and that's consistent with when we checked. When we used dx, it was too small. It was way too small. So we want to use ds instead. So we can't model the surface area with just plain old cylinders, because those edges of those cylinders stay horizontal and it doesn't work. So we need a different kind of element to model surface area than just the same cylinders we use for volume. We can't use those volume cylinders that we did anymore. All right, so let's take a look at what we can use, which will work. So if we take a cone and we cut it open, we get a shape like that. If we take part of a cone, so that's called a frustum. A frustum, take part of a cone and flatten it out, we get this shape like this. It's kind of like a C. All right, and so that shape right there is what we can use instead of just the rings on the end of a cylinder, just like a plain right cylinder. We actually have to use a cone, part of a right cone, to do this surface area modeling. So again, we just take a chunk of a cone and we flatten it out. And this is going to work for us to model surface area instead of just the circumference of the cylinders we used for volume. Okay? So here this shows that. Here's delta x of 1 using those, what we call frustums. Frustums, not, do you see how they're angled now? According to the curve instead of horizontal. Here's a smaller delta x of 0.5. So let it run here. So do you see how, and each of those is like a cone that's been chopped, right? And then here's a real small delta x. And so now we see that the edges of those frustums, or those little pieces of a right cone, can model surface area correctly. Yeah. All right, and so again, we want to use ds, not dx. We want to use ds, that hypotenuse of that little triangle. And so we want to take that thing, that frustum, right, that part of a cone. We want to flatten it out, and that will allow us to get the right rate of change. So here we are. So this is what you get when you take a part of a right cone, and you cut it and you flatten it out. This dimension is then ds, little s, right? So that's our arc length. It's like the hypotenuse of that triangle. And what we want is all this gray area, which is d capital S, right? It's going to be our element for approximating area. So what's the perimeter? The perimeter of the thing is 2 pi f of x, so we already have that. But now we got to multiply that by ds. So imagine this as like a warped rectangle, and we're just going to do length times height of the rectangle. It's just in a circle now. So that area, that gray area, is just going to be the length around times the other dimension, ds. And that's the same ds that we found for arc length. Is our hypotenuse of our triangle. So what was that? That was the square root of 1 plus the rate of change of f squared dx. So there it is. There's our rate of change of surface area. So it does have the 2 pi y that we came up with, but now instead of just being 2 pi y, 2 pi f of x dx, it's 2 pi f of x ds, right? It's the ds now instead of just dx. So then there is our rate of change of surface area. So this accounts for changing it from the horizontal piece to an actual angle piece, like the hypotenuse of that little triangle, to match the curve. So now let's go back to our sphere and see if it works. Up here. All right, so we want to change the. Now we want to change the rate of change of the sphere, or sorry, the accumulation. The HS is half sphere. What do we want to do now? So see if you can. I'll call a few more names. We want to change this accumulation function so that it'll be correct now. Change it so it'll be correct, and then check with the people around you. Okay? Go. Okay, spin the wheel. Oh, shoot. Or Anley. So is Anley here? Did you come up with the new rate function? Or the new accumulation function? Okay. Okay, did you say square root? Square root of? 1 plus r of. So we're going to define that function, right? Let's see here. F of what? S? Let's use t. We usually do. Okay, and then squared. Let me make sure I got that right there. I don't know if I got that right. So R sub F control. That's better. Okay. So 2 pi y, 2 pi f of t, right? And then that's our distance around the frustum, and then this is that, instead of dx, that's the horizontal, that's that distance, this distance. Okay, so when we flatten out the frustum, that's our ds. And then this distance around is our circumference, 2 pi y, or 2 pi, in this case, f of x. Okay? But we need to, if we're going to, what's wrong?
We need the rate of change for
Yeah, so we haven't defined rate of change of f. GC can't read our minds. If you're going to use r sub f of an r sub f function, it's got to know what r sub f is. So I'm going to define that. And what is that? That is, so we could do that manually if we wanted. We could use the chain rule, right? Or we could, again, use the, yeah, let's do the chain rule. What is the chain rule here? It's going to be 1 half.
9 minus x squared to the negative 1 half.
Yep. And the denominator. Remember your chain rule. Don't forget. Is that it? Then times
3 minus 2.
times negative 2x, right? Okay, so we come back down here and look at the surface area from 0 to 3. Now that we have the right surface area function defined, and it's the same as 18 pi. It works. Any questions?
Why is it 0.4?
Because it's just using a numerical method. So this would be exact, but in order to actually calculate the integral, it's actually taking a really small delta x and doing a sum. So that's how calculators actually come up with approximations. They accumulate as if with a really small delta x. So that's why it's off by a little bit. Okay, other questions? So I owe you time. This is about half the time I owe you.